a microgrid commissioning case study that Alex Mathers from GMC Commissioning will walk us through. A few words on our speaker before we get started. Alex is a founding principal at GMC Commissioning Incorporated. He spent the last 4 years building GMC Commissioning into the largest dedicated commissioning firm in California, specializing in highly technical, complex, and critical facilities. So without stealing any more time today, I'm going to hand it off to Alex to kick us off. Alex?
Thanks, Sam. Let me share my screen. All right. And let me just do this. Hi, and thanks everyone for joining today. My name is Alex Mathers. I'm a owner of GMC Commissioning located in San Diego. Joining me today is Joe Abadaltif, who was the CXA on the project. Today I'm going to cover a unique project we recently completed called Sharp Rees-Stealy, which included a 400 kilowatt microgrid. Sharp Healthcare is one of San Diego's largest healthcare providers, and the Sharp Rees-Stealy Medical Center project was an 86,000 square foot new ground up medical office building in the city of Santee, California, which is located in San Diego County. The microgrid was included in the project based on a projected utility savings of $300,000 annually. This is an AIA continuing education system course, and to comply with requirements, they'll be accompanied 10-question quiz, so make sure you pay attention. I think the quiz will come later on. This presentation will focus on 5 main topics, which are the types and benefits of microgrids, the setup and operational modes at Sharp Santee, the challenges of testing the microgrid, the commissioning issues found and fixed, and finally, lessons learned and recommendations. At the end of the course, if I did my job well enough, I hope you will have a basic comprehension of microgrids, be familiar with the various microgrid operational scenarios, and understand real-world issues with the testing and implementation of a microgrid. But first, just to make sure everyone's awake and paying attention, we have our first of 3 polling questions. So the first question is, how many of you listening today have worked on a microgrid project? This is a yes/no question, and I think, yeah, the poll should pop up, and we'll see what the results are. And, oh, okay. So we've got 11% yes and 89% no. So that's a fair amount that have not worked on a microgrid. So hopefully this presentation will help everyone going forward. All right, starting off from the top, what is a microgrid? A microgrid is a small, local, and smart energy grid. A microgrid generally operates while connected to a main utility grid, but it can break off and operate on its own using local energy generation or storage. The microgrid must have smart control capability to disconnect from the utility grid and operate autonomously. This is called islanding. A microgrid can be powered by distributed generators, batteries, and renewable resources, which means it can take advantage of many different distributed generation technologies such as wind turbines, solar panels, diesel generators, and a few others. The more electrical generation that is interconnected in the microgrid, the more resiliency can be achieved. However, the intermittent nature of renewable resources makes the operation of the microgrid more difficult. Therefore, energy storage devices are necessary to smooth out that power generation of these intermittent sources. Finally, a microgrid is not just a secondary or distributed energy system. It's not just a rooftop solar panel installation or just a backup generator. It's designed to supply power, primary reliable power, 24/7, 365. Depending on how it's fueled and how its requirements are managed, a microgrid might run indefinitely. So there are 5 main benefits of microgrids. The first is a microgrid improves electric reliability or energy resilience. In the case of our project, the Sharp Rees-Stealy building, microgrid provides backup power to select emergency loads during a power outage. This is important, obviously, for a hospital or medical office building. Having that reliability, that backup, is obviously a big benefit. Second one, a microgrid can lower energy costs for consumers and businesses. In the case of the Sharp building, microgrid offset the building's energy use via the solar photovoltaic system. It also lowers utility demand charges with the battery energy storage system. And I'll get into that a little bit later. The third item is that it's more efficient because generation is close to the demand. So a microgrid is more efficient than, say, a distributed utility because that the power generation is physically close to where the power is being demanded from. So you're removing that transportation loss of a typical utility where you might have, say, coal-fired power plant or gas-fired or nuclear power plant miles and miles away, and have to transport that energy, across power transmission lines to where it's actually being used. In the case of a microgrid, obviously you've got that power being generated right there, right where it's being used, and so that's one of the main reasons why it's more efficient than a typical grid. The fourth benefit is a microgrid strengthens the central utility grid because less energy is demanded from the local utility as a solar voltaic system operates, and less power is required as a battery energy storage system clips or curtails the power demanded during peak periods. Finally, a microgrid brings economic value to society. Microgrids offer economic value. They avert loss of product and work during power outages. They attract high quality employers to a region, and they keep jobs within a community. Now I'll go over different types of microgrids and for different project types. So there are obviously different types, multiple different ways you can set up a microgrid, and there are different configurations for the different project types. So I'll cover four of them here. Obviously there's more, but I'll just talk about 4 here. First are military or other projects where power availability is a security concern. Microgrids provide the ability to reliably incorporate solar energy storage, diesel generation into military energy systems. This independence is a critical objective for the United States Department of Defense. Reliance on diesel fuel in remote regions in the world is a weak point in military operations, and the results can be costly due to the challenge of transporting fuel through hostile regions. Another example of a microgrid is a campus system. Not all microgrids use solar as their prime generation technology. Campus microgrids, for example, many colleges, corporate campuses, they're incorporating microgrids, and they use combined heat and power, where you've got a gas turbine, which generates power with its exhaust connected to an absorption chiller for chilled water and a heat exchanger for domestic and heating hot water. And so if you have a collection of buildings that are close to each other and they all need chilled water, they all need power, and they all need heating hot water, it's obviously more efficient, more energy efficient and cost efficient to have a microgrid which can produce all of those different utilities there on site. The third type is remote projects. Microgrids are attractive to, I spoke earlier about islanding, but they're attractive to literal islands due to the high cost of importing liquid fuels. So while traditionally run off diesel, small and large islands around the world are incorporating renewables and energy sources, energy storage into their energy systems. What makes these different from other types of microgrids is that they're not grid connected. There's no other utility grid. They are themselves on an island, and they are always in that islanding mode. Finally, you can have multiple footprint projects where network microgrids or nested microgrids which are several separate microgrids connected to the same utility grid circuit, serve a wide geographic region. Networked microgrids are typically managed and optimized by a supervisory control system, and operate and coordinate each grid connected or island mode at different tiers of hierarchy along the utility grid segment. Okay, so now with some background, I'll return to our project that we're here to discuss. A little bit about the Sharp MOB. So Sharp Hospital, the owner started in 1955 as a nonprofit charitable institution providing general care for San Diego County. Today they have 3,000 physicians, 18,000 employees working in. They have 7 hospitals and 3 medical office buildings. This Sharp medical office building in Santee is their newest building and offers primary and specialty care, urgent care. They have a pharmacy, laboratories, radiology, among many other services. So here I've created a kind of a cartoonish, but just a basic diagram of how the Sharp microgrid was set up. So just to go through it, and let me see if I can do a laser pointer here. There we go. So the Sharp Santee microgrid is 400 kilowatt DC, 300 kilowatt AC system, which includes 950 LG solar panels. They're rated at about 400 watts each. These are wired in series of 18, connected to 6 inverters, DC to AC inverters, with integrated disconnects. These solar inverters are connected to an 800 amp panel board, which is this DG2 right here, which is also connected to the Tesla battery pack, which has a 140 kilowatt inverter and a 16 pod battery pack, which can store 225 kilowatt hours electricity. The Tesla inverter is a grid forming inverter, which means it's responsible for creating and maintaining the voltage and frequency of the microgrid, and it ensures that excess power is tightly synchronized to the grid. This DG2 panel board is connected to a 1200 amp panel board DG1, which feeds emergency loads in the building. So here diagrammatically, I'm showing 2 buildings. There's just one building, but that one building has emergency loads and normal loads. Here I'm showing 2, but in reality, it's just one building with the different types of loads. So DG1 serves the emergency loads in the building. It's fed by, this DG1 is fed by motorized breaker panel DG3, which houses connections to the grid, the utility grid through CB1, and to a 100 kilowatt diesel generator through CB2. CB1 is connected to a 3,000 amp main service board, which houses incoming utility service power and normal loads to the building. And there are a number of power meters along with the system that I'm designating here as M1, M2, M3, M4, M5, M6. And I'll get into those in a little bit. But these power meters measure the flow and direction of power in the system. The system is paralleling, which means synchronous operation of multiple power sources connected on a common bus to provide power to the loads, to the normal loads and emergency loads. There are 4 other main items, which are the non-export relay, the generator controller, the NL site controller, and the islanding controller. So the non-export relay, this makes sure that the Tesla battery does not output to the grid. It does this by monitoring meters M6, M3, and M4, and it makes sure that power going out through M6 is less than power being used by M3 minus power being brought in through the solar through M4, which is the available power to normal loads after taking into account the solar power produced. So the main purpose of the non-export relay is to make sure that the Tesla battery does not export power to the grid. Next, the generator controller. Obviously, it starts a generator, it controls a generator, it's able to vary the frequency of the generator output, and it synchronizes to the grid. The NL controller uses the facility utility rate structure to determine when to charge and discharge the battery. And finally, the islanding controller ensures the microgrid emergency power remains energized during a power outage. Another note is that there's no true ATS. The motorized breaker panel DG3 has these 2 breakers, CB1 and CB2, interlocked. So there's no ATS because both of these breakers have to be able to be open at the same time. However, they can't obviously be closed at the same time because we can't export generator power to the grid. So similar to the battery, we can't export battery to the grid, we can't export generator power to the grid, we can only export solar power to the grid. Here are some images of the project site to kind of relate what I was just talking about in diagrammatic fashion to what was on site. So first picture here on the left, there's a building, whoops, in the background, and there were solar powered carports or shade structures here in the parking lot. There was also solar arrays up on the roof of the building. This is the Tesla battery pack and inverter, which was out here, mounted out here in the parking lot. On the back side of that is the NL controller. Here's another picture of the solar panels above the parking area with the inverters. Behind the building, back behind here is the generator, the 100 kilowatt diesel generator in a separate structure. Inside, on this side of the building, is the electrical room, which houses, this is the motorized breaker panel with CB1, CB2. There's also other meters here. This is the main utility meter. And this is a picture of the non-export relay. So one of the main purposes of the microgrid is to save money. Obviously, there must be some payback. The way Sharp is able to reduce utility costs is to use the local utility, which is SDG&E here in San Diego, the rate structure to its advantage. SDG&E has 8 different rates depending on time of day, also known as TOU or time of use. Also different rate structures for the day of the week and the amount of usage. They have rates for on-peak, off-peak, and super off-peak. There's also a baseline allowance, which you can see here. for the monthly amount of energy you can use at the lowest tier pricing. So if you use more than your allowance during your billing cycle, you'll move up to the higher cost tier pricing. But because SDG is so nice, they provide customers with an additional 30% of their baseline energy before you actually go into that higher rate. So the rates could be anywhere from 19 cents to 35 cents, 30 cents to 57 cents, depending on, like I said, the time of day, day of week, Monday through Friday, or is it a weekend or a holiday. And all of this, all these rate structures was built into that NL site controller, which determined, and I'll get into that more in a little bit, but determined where power is being used from. So just to take a little break and make sure everyone is still awake, I've got our second polling question number 2, which is an easy one, also a yes, no. Who else has clients with similar utility rate structures, or if there are any owners in the audience, who else has a similar rate structure to the one that is here that I just went over? You should see, yep, there's the poll. And all right, results 39% yes, 61% no. So all right, that's interesting. I would expect more people did, but probably going forward, more people will have those rate structures as utilities get more complicated. So I will move on to, so this slide, just kind of going back to the diagram, I'm not really going to dive into exactly what the wiring, but here's just an example of how the communications controls for the microgrid are decentralized. So this means the intelligence for the system is distributed. There's no one central brain. Like I said before, there's the non-export relay, there's the NL site controller, there's a Tesla controller, there's a generator controller, there's the islanding controller. So this means that there's many different controlling components that need to work together safely and efficiently. And that's where we as commissioning agents can come in and help make sure we test through all these scenarios because there's so many things, so many different pieces and parts to it to make sure that it operates smoothly. So what I'm going to do now is talk through the different operational modes and sequence of operation of the Sharp Santee microgrid system. So starting off on a normal operation, a sunny day. So the sun is out, power from the solar array supplies power to DG2 through the DC and AC inverters. Available power at DG2 from the solar panels is used to charge the Tesla battery. Any extra power then goes to DG1, which serves power to the emergency loads. DG1, then any more available power goes to DG3, which is the two circuit breakers, CB1, CB2. CB2 is open. CB1 is closed, so power is going back up here to the main service board and then serving normal loads. Any additional power is then sent back or exported to the utility, and then Sharp is paid monthly based on how much they're able to export through that. M1 is a utility meter, so how much power they can send through that utility meter, they get a monthly amount from the utility. It's not a lot, it's kind of pennies on a dollar, but it's some. It's better than nothing. So that's normal operation on a sunny day. So now let's say it's clouds come in, block the sun a little bit, power from the solar array still supplies power to DG2, which can still charge a Tesla battery, supplies power to DG1, sending power to the emergency loads, sending power back up here to main service board. Maybe there's a little bit more to serve the normal loads, but not enough. And in that case, now we're bringing power in from the utility just to offset any additional power that we will need. Now, let's say it's a fully cloudy day. Obviously, here in San Diego, it never happens. I mean, I don't know why we'd even have to test this, but let's just say we've got a cloudy day here in San Diego, and we've got minimal power coming from the solar array, supplying power to panel DG2. Now, since it's not enough, and since it's during the day where we're on peak, and so now the NL site controller says, hey, it's a good time to use that stored energy in the battery. So now we're supplementing any power from the Tesla battery, sending that to DG2, to DG1, sending it to the emergency load, sending it back up the chain, and sending it to the normal loads of the building, and then importing any additional energy we might need. And so here's where the non-export relay will throttle the Tesla battery export so that meter M6, like I said before, doesn't exceed meter M3 minus M4, which is again the available power to normal loads after taking into account any solar power produced. So power supplied to the building normal loads, but not enough by design. And then any additional power is brought in from the utility. All right, and let's say we're at night, we're say a super off-peak time of use. There's no power from the solar array, but that NL site controller knows that it's a super off-peak time, and so now it's charging the Tesla battery from the utility and also serving normal loads, emergency loads. Basically taking as much of that cheap energy as we can during the night, during that off-peak rate structure to serve loads and to charge the battery. Now, let's say now things get interesting. Let's say there's a loss of utility power. So the system or the utility power availability is monitored at this meter M2. It's looking at voltage on the line on the main service board. So utility power is lost, the building normal loads are dropped, the solar inverters turn off, the islanding controller then opens breaker CB1, which islands the system. It kind of creates that point where now the system is just the generator, the emergency loads, the battery, the solar panels. And then the Tesla inverter starts forming the grid. It creates a grid for the emergency loads. Now it's, let's say all that happened and it's a sunny day. So we've lost the utility, everything, like I said, happens, the normal loads are dropped, solar inverters turn off, Tesla inverter forms a grid, islanding controller opens breaker CB1. Now the Tesla battery supplies power to panel DG2 and provides backup to the emergency loads only. Tesla is also now monitoring the solar generation, and if it's too much, it will shut off inverters to curtail the inverter output. So there can be a case where there's too much solar, and the Tesla controller is monitoring that. If it's enough, it will start to let the solar panels power the emergency load directly. But first, to make sure the emergency loads don't drop, the Tesla battery pack is providing that power as soon as it can. But let's say there's loss of utility and now there's no solar. It's a cloudy day, or maybe it's at night. The solar inverters, again, they turn off, and Tesla inverter forms the grid. Islanding controller opens breaker CB1. The Tesla battery supplies power to panel DG2. Tesla battery provides backup to the critical loads only. Tesla is monitoring the solar generation and sees that there's zero power at meter M4, and the Tesla controller provided battery backup provides that battery until it reaches about 40% capacity. So it drains the battery, its batteries down from 80, 90%, whatever it was, down to 40%. And then it sends a signal to the generator controller to start the generator. This that 40% number, it's adjustable, and that was dialed in during testing. I think originally it started at 60, and we were able to drop it down to 40%. And so the test controller provides battery backup until it reaches 40%. Then it sends that signal to the generator controller to start the generator. The generator controller is paralleling and also grid forming. The controller modifies the engine governor speed until it gets to 60 Hertz. The generator controller then closes breaker CB2 once up to speed. CB1 is open, CB2 is closed, allowing the generator to provide power to the microgrid system. And then it runs. The generator provides that backup, charges the batteries while it's doing that. Another note is that the generator is also programmed to come on if, for whatever reason, the Tesla battery fails. That's another fail-safe, is if, for whatever reason, Tesla battery fails, the generator will automatically come on. So once the generator comes on, supplies power to emergency loads, and it also charges a battery. It'll charge it up to about 60%, and then leave it there. That was also another thing that was field adjustable. So this happens until utility power is restored. Upon restoration, the islanding controller synchronoscope measures waveforms between the Tesla and utility and allows breaker CB1 to close after 5 minutes to verify synchronization. So similar to an ATS, it's looking at what's available on the emergency side and what's available on the normal side, and it will make that transition after 5 minutes. Tesla will not give the islanding controller permission to close breaker CB1 while the generator is running. The generator will run for 15 minutes, and then Tesla commands breaker CB2 to open. The generator enters a cool down mode, but it does continue to run. One thing I'll get into a little bit is Tesla doesn't allow the generator to, or doesn't turn off the generator. It turns it on, but it won't turn it off. All right, so how did we test this microgrid? Well, first we brought in specialized subject matter experts. We assigned our top commissioning agent with experience in complex electrical systems. We held a number of multiple commissioning coordination meetings on top of regular MEP coordination meetings or OAC meetings. We had testing plan meetings. We held multiple testing meetings around our testing plan. We developed unique testing protocols to match the scenarios that I just went through. And as far as execution, we had to test at all different times and conditions to match the scenarios. So we had to test at night, during the day, when it's sunny, when it's cloudy. All that had to be tested to make sure that the microgrid operated as intended. We used, for this project and all the projects, we used Facility Grid to track the issues and collect responses and close the items that we found. Here are some of the issues that we found and we fixed. The first one is that the utility motorized breaker CB1 was wired incorrectly with the non-export relay due to drawings being incorrect. The second item was the generator controller issues. The generator was tripping out on reverse power, which means the engine was not producing sufficient torque to keep the generator spinning at its rated speed. So the generator frequency was increased to prevent trip off when paralleled with the battery and with solar. Third item, the island control panel was internally wired wrong, which led to additional 12-volt relays needed to be installed to properly work with the motorized breakers and a generator controller. The motorized breakers interlock need to be hardwired so the system can't export generator power to the grid. Directional electrical meter current transducers, or CTs, we found they were installed incorrectly. It was a simple fix, but they were just installed the wrong direction. They had to be turned around so they were in the correct direction. Once utility power is restored, the generator continues to run. So talked a little bit about this earlier. So Tesla doesn't want the responsibility of turning off the generator. Once utility power is restored, the generator continues to run, and it requires manual intervention to turn it off. The load is transferred, everything works fine, but again, this could be in the middle of the night on the weekend, generator will continue to run until someone comes in and shuts it off. This was something that they went back and forth with Tesla on, trying to come up with a fix, and in the end, or still today, that's how it is. There's no simple answer to turn off the generator. Even though it's in cool down, there's no load on it, but it will continue to run. And the next issue found is that there was too much power in the system when islanding, when there was a full sun. So the solar inverter curtailing sequence, when on microgrid mode or island mode, was originally set to power up the microgrid with all the solar inverters on at once, and then power them down one by one over time. But there were issues at utility power loss and full solar generation. Voltage was building up on the line and exceeding parameters and tripping the battery. Tesla was then sending the generator start signals since it was tripped. The thing to note is that solar, since it's a current source, you can't really interrupt current instantaneously. So the inverter restart sequence was delayed by 10-second intervals and brought on one by one so curtailing could go into effect. So instead of trying to stop all that current from the solar, they just started with bringing on the inverters one by one. Finally, if the battery system fails during a utility outage, the microgrid will not automatically reconnect to the utility grid once it's restored. So if there is a battery failure, CB1 stays open. There's no way to automatically transfer emergency loads back on restored utility. This also must be done manually. Some of our lessons learned from this project. First, when designing a microgrid, the sizing ratio between the battery and the power generation is custom. It needs to be engineered and optimized. So my understanding is the battery is typically sized to from 1 to 1.5 times the generation capacity. In this case, the battery was sized, it was a bit under, I think, 1 times the generation, but that's, again, that's a custom and engineered sizing ratio. Second item is that the motorized breakers or the remote breakers, like the CB1, CB2, they're not foolproof. With no mechanical interlock, anyone can click close on the breaker because it's just a controlled interlock. If someone shuts a generator motorized breaker, the breaker will command close and trip right away, and will also trip the generator output breaker. Next item is that obviously microgrids are not a tack-on item. It's important to incorporate microgrids in the design early. In our case, for this project, the decision to move forward from Sharp Santee came in a little bit late during construction. This wasn't a decision that was made early in design. So final drawings were received only about 2 weeks before we really started functional testing. Next thing is that proprietary information is challenging. We had limited support from Tesla, and it was hard to get information due to intellectual property concerns and limited documentation. Because this is still a new system, it's hard to get that information, especially for us as commissioning agents, to properly set up our test, figure out the sequence, and execute on that. Next lesson learned was battery integration is not really a solved problem. There are a number of sequencing and control items that need to be engineered for every project. Every project is unique, every project is different. Tesla's still working out a few solutions for their system that currently require human or interaction, like I mentioned before, to correct as previously discussed. And finally, just because you're ready to test doesn't mean the team is available. So we were there ready to test, but Tesla wasn't. They weren't readily available to commission their battery bank when it came time for us to do our functional testing. So a couple of notes on adding value. So we create value for our owners by using their investment in the commissioning process to save them money in the future. The benefits of our work include energy cost savings. So by dialing in those adjustable set points, we were able to enhance the performance of the microgrid system. Fewer change orders during construction. Through design reviews and submittal reviews, working with the owner, we're able to help align the results to the owner's expectations. Reduce project delays by coordinating the design, the installation up front, and through the vendors, we're able to remove potential bottlenecks. Better communication among the project team, additional commissioning meetings allowed for more interactions and quicker resolution to solutions to issues. Higher system reliability. The reliability of a series system is no better than reliability of the worst component. By finding and resolving the weakest link issues during testing, the resulting system was more resilient. And longer life cycles for building equipment. So by dialing in those adjustable set points, like I mentioned before, there's less short cycling. Also ensuring facility operators are trained on proper maintenance and operation increases the likelihood of improved equipment lifespans. Some of our recommendations for improvement: better technical support and coordination, heavy controls integration meetings required from the start. For some contractors, it was their first microgrid. Some had battery storage experience, but not a lot with generators. So making sure that obviously everything is coordinated early on is a huge recommendation. Work hard to get direct support from vendors during testing in a timely fashion. Like I mentioned, there are vendors not only from Tesla, but the controllers, the generator, making sure that you get that support when you need it when you're doing the functional testing. And finally, obviously start planning early. Trying to help the owner make decisions early, ideally in an OPR. This project was not a one-off, or this project was a one-off, and a 3 months decision delay resulted in a squeeze in installation and testing at the end of the project. So it's not, microgrids obviously are not a plug-and-play system. So final polling question, take a moment and think, how would you test this microgrid? How would you manage the testing schedule for this microgrid project? So if you were in our shoes and you had limited time to prepare, drawings are incomplete, there are multiple vendors and parties, but the owner had a strict turnover date with liquidated damages. So no matter what, there's a drop dead date of when the system had to be ready, had to be safe, had to be efficient. Most, if not all, testing had to be live with significant PPE required, lockout, tag out, strictly enforced. Testing off hours at different times of day, like I mentioned. This is our last polling question. So would you request additional time from the owner, or would you work overtime to complete on time? This is something obviously not just for this project. I'm sure everyone has come across this in other projects. When you get caught at the end between drop dead date and all the work that you have to do. I'm curious how people in the audience might manage this testing schedule. And all right, 30% say request additional time, 70% say screw it, we're working overtime, we're doing everything we can to complete on time. Not that there's an easy or correct answer, but that's great feedback, and I definitely appreciate it. So that's the end of my presentation. I think we've got some time left for Q&A.
Yes,